Now I want to actually divide the piles as I did here. So if I come to this line, what I need to check is the local axis. So let's have a look at the local axis at first. So I'm coming local axis for frame, and I apply it. You see, because I draw the element from top to bottom, local axis is reverse. Generally local axis should be bottom to top. So what I need to do, simply I can come and select all piles by section. So I'm coming to select and properties, frame section, and I'm coming here and choose pile, and I select them. Then I can come to assign, and I'm coming to frame, and then I'm coming here reverse connectivity, and you can see here what will happen. So all of them would be upward now. That is including these points. We cannot see them, but all of them change now. Now again I choose previous select, and I'm coming to divide and choose exactly the same and apply. So now if I go to this plane, which is XZ plane, and this is Y17, and I'm moving up, you can see other pies, all of them are the same. So you see we cannot actually see the pies we draw here because they are not exactly on the grid line. So what we need to do, we need to select one of those joints, which is here, and then come to edit points, and add grid line, edit intersection, constant Y, and apply. It still is not possible to go there because this is a secondary grid. As I said, it's not a primary grid, so you need to come to edit grid data, modify show, and find that grid line in Y, which is here. So between 7 and 8 we can name it 7A, and we can put it start, and it's primary, and then OK and OK. So if I come here and move back, now I can see the pies here. So I define all my pies. What I need to do, I need to assign the spring stiffness. So for the first part up to Z-7, it's in the stiff clay. So we don't have any vertical stiffness, we have just lateral stiffness, and lateral stiffness for this area is something around 24,000 kilonewton per meter. So what I can do, I can select all pies. I need to select them based on the Z level, or I can go and select them one by one because there are not too many, so I will select them. But as soon as I select them, I put them in a group name, so I don't have any problem in selecting them again. So I'm selecting all those piles. Now I need to select two other piles for the wall. So if I zoom out, I need to come to YZ direction on grid F. So staying here, YZ direction, and this is grid C, so I need to move forward to reach to these two. So all frames are selected, just a point here, it doesn't change anything, but you can just have the frames. Now we need to go to define and define new group name. So I'll put add a new group name, so it could be pile 1 and pile 2, for example. So pile 1 are top piles. It's really up to me what name I prefer and it's more convenient for me. So pile 1 and pile 2, and I keep them. Now I can assign to group. I'm coming here and I select pile 1, and that's replace is okay. Now I can select all piles by section, frame section, and choose this. So all piles are here. If I put show selection only and make it more clear by disabling grid line and then coming to 3D, if I zoom in, you see all piles are selected. So I can come here, deselect group pile 1, deselect. Now just below piles are selected. Now I can assign them to pile 2. So I'm going to assign to group pile 2, apply. Now if I come here and say select group and pile 1, so all top piles are selected. Now I need to define line spring. So I actually need to come to frame, assign and frame, and then come to line spring. And here for stiff sand, the lateral stiffness is something around 20,000 kilonewton meter per meter. For that 600 pile. Just bear in mind the lateral stiffness generally they give you, the geotechnical engineer gives you, is not the way of applying this stiffness is not like that you need to apply to the projected area of the pile. For example, if the pile diameter is 1, is multiplied by 1. If it's 0.6, is multiplied by 0.6. They always play with the stiffness in the way that at the final linear stiffness would be the same. Doesn't matter what's the diameter of the pile, 0.45, 0.6 or 1 meter or anything else. Don't ask me how it happened. I'm not a geotechnical engineer, but I know generally this the result of multiplying any specific stiffness of each size of pile to the diameter of the pile would be the same. So when the diameter of pile decrease, the stiffness increase. So we using tension and compression again because we don't have non-linear option. The good thing here is when you apply a spring in one side, so when you move pile, for example, along axis 2, if it become far from the spring, a spring is under tension. If become close, a spring is under compression. But the reality is because the pile is confined, each side you have the same compressive stiffness. So that 20,000 would work. Actually, tension in one side act as a compression in the opposite side. So you can keep this number. It's perfectly fine. You don't need to make it half like what we did for retaining wall. And we have few options here. Again, we can go for parallel to line object local axis. So you can choose local axis 1, 2, 3 or a negative side 1, 2, 3. So we need to apply a stiffness in two directions, 3 and 2. So we need to add them together. Or you can use the coordinate system, as I said before, local or global. It's perfectly fine because this local axis is matched with the with this one, but currently we can go for this. We use local 2 component and we can put, for example, factor 1, and then we apply. Again, I select the same part, so previous selection, and coming and applying to local 3, 1, and put this one 0, and this one this time I need to add to the existing spring. So apply, and then I'm coming here, select by group, coming here, group, and then selecting pile 2 group, and do exactly the same with the different stiffness. So this group of piles are going into class 5 sandstone. So the lateral stiffness is something around 40,000 kilonewton per meter, just some rough numbers. So this is fine. This we can apply at the beginning to local axis 3 component. So apply, and again previous select, and then I'm choosing 1, 0, and then I need to add to the existing and apply. Now what is remaining is the end stiffness of the pile. So if I can select them in plan for z-10, but because the numbers are not too many, I can simply select them here, and I need to define the stiffness at the bottom of the pile. So the stiffness of the bottom of the pile for class 5 sandstone, the vertical stiffness is something around 80,000 kilonewton meter per square meter. I need to multiply it by the area of the pile, so that would be something around 22,620 kilonewton per meter. So those are points. I need to come here to assign, go to joints, and use a spring here, and then I need to put in what translation 3, the number is 22,620, and yes, it's add or replace, doesn't matter, so you can apply. So the springs are here. So that's how you can support your structure. So laterally and vertically, pile actually is supporting the whole structure. For the wall, retaining wall, still what you did is valid because you have the soil surrounded, and the building is confined from ground floor below. So this is basically how we can actually apply the stiffness and how we can model the piles, and we just need to replicate those and do the same for the other walls and other elements. This is enough for you guys to see how you can model the piles. Next module would be about loading, and I will complete these models and I will show you how to define loads and apply loads.